So I forgot. I totally. This is horrible because I'm like, it's costing me so much to try to remember where I was just barely a week ago. It's like I don't do these videos that often. So how to basically remember where I was, what I was doing. I remember. I think what I was doing is basically basically the loss is not going down, right? So we're looking at the loss function, we're looking at the derivative of the loss function, and we're looking at what are we looking at? Moment properties SGD in the backward. Maybe that's. I think Oh yeah, I remember now. In the backwards function, does it go there? Yeah, the backwards function. So yeah, so I was looking at why are we involving A1 at all? Why don't we just do this with W2 directly, right? Yeah, we spotted that M equals 1 could have been an issue. Because M here was set to the shape, which is the vocabulary. In this case, was the vocabulary size, and we don't want that. Then, exactly, we're thinking at like, why are we doing these with A1 at all? Why not directly with? Because essentially, bro, I started to switch on my brain. Essentially, what we get out of these at one, it's telling you. So if y, so this is predicted, and y is the ground truth, right? Just doing yeah, I wanted to make a small example. That's what I wanted to do. A small example with a small vocabulary, something that we could visualize easily. Notes. Yeah, that's what I was doing. I was saying if we are doing the prediction, if we're doing prediction minus truth, right? Because that's what we're doing. Doing prediction minus truth. And so we basically have something that it's almost just like all zeros, and then if the prediction is wrong, we get a 1. If the prediction is right, we get a 0. This means don't do anything, right? If the prediction is wrong, as in like it should be a 0, but it's a minus, but it should be a 1, but it's a 0, then we get a -1. And that is fine. That is fine because then later on, these learnings are kind of like minused, which is kind of the correct thing to do. But now, what I don't understand is why am I doing it with a what am I doing here with A1, right? So so what is this doing really? This is doing a What is this doing? It's reshaping A1 to be of shape, this shape. So Ghostwriter, help me here. So in NumPy terms, something of shape XY I know it's stupid to ask vertical, not vertical, horizontal. It just helps. It just helps mentally. So it's like X rows, Y columns, or the opposite. X number of rows, and so this is a column vector because that's one column. So it does A1. So let's basically first of all study what is this here, what is happening here, right? So we've got Z1, A1, Z2, and then logits. Got these different components. So no, W1, W2, that's all we have. Okay. It's like E1. It's like Z1. But we have W1, so we have the sort of the first layer here, W1, which is input size, hidden size. So this means so the input size, the input size, the input size, the input size. What is the input size? So what is the difference between array? This is like, I get it, because this is basically saying hidden size columns. No, rows, hidden size rows in one column. So this is synchronous. So what I'm trying to say, what I'm trying to see is, so let's try to recreate these. Okay, let's try to visualize these. I'll recreate. Just so we understand better what is it that we have here, right? So something like this. So we're having, so we're just having input size. Let's say it's whatever. It's like 3. Size. It's like 10. Why would you do 10? I don't know. No, maybe we'll do 10 and then we'll do hidden size 5, and then output size yeah, 3. Okay. So don't have the self concept here. Give me go to pretty print tenses like W1, 2, and B2, and test.poly. That's not very pretty. Pretty, I think. Let's see what it does though. Python. Okay, no, not bad. Let's actually do a good enough job. So we kind of have something like W is like basically saying 10. It's like 10 by 10 rows by like 3 columns. Okay, and then B1 is just 5. I guess what happens if you do like, so if I add something like this, and then I say one, like how's this executed? So that just it cannot easily broadcast, or it can just because of the dimensions, I guess. Hasn't done anything really. So it's interesting, right? So this is not really actually doing anything at all. Of course, you want plus then. That's all we want to do. Basically, just have these things like that. So it adds 10 everywhere. It finds a way, it kind of finds a way to do it. If B1 was of size 3, so I hope I'm not paused. Well, so if I would do something B3 that is not hidden size, but it's input size, so, and then we would just do B3. Well, it figured it out as well. Interesting. It doesn't. It really it really does. I mean, how does matrix addition work? the shape preconditions. Broadcasting, okay. With the same, fine, yeah. But now, perform addition operations on tensors that do not have identical shapes by broadcasting the small tensor over the larger one. Instead of broadcasting takes a small tensor and repeats it alongside its axis to match the shape of the larger one. The broadcasting rule in NumPy is that for tensors that are broadcast together, the size of the trailing axis for both arrays and the function must be either the same size. So one, okay, so broadcasts these through, kind of has top to bottom, so to say. I mean, that's just difficult to remember anyway. But it does so, yeah, okay, so it's doable. So it's doing these kind of broadcasting, okay, to like this is kind of what we have. So we've got W1, W1, B1, W2, B2. That's all good. Okay. So now, and when we're doing this, we're kind of having an in between Z1 that does these and A1, right? It's basically a combination of I've got an input. This input gets multiplied by W1. You're adding this bias, and then basically A1, yeah. So can you see if I take these now? So this is kind of like simulating the forward pass. So is there a way? So okay, so we're missing obviously X. So X is just the input size, right? And I think essentially what were we doing with this input? Whatever, something of the input size. I know we're pre-processing these, but like X size, well, essentially X equals input size. And then grid bin X. That's good prediction there. Okay. Grid bin X, exactly. And then we've got Z1, Z1, and A1. Just so with X, we just have something that looks like that. Transposing it, it means turn it into a column. So if I'm doing these, then it turns out I just have so what about I just do X and then expose treats it the same, but I mean, think printed the same, but I think the shapes will be different. Won't they? Actually have to print the shapes. This will definitely be different, right? Is it because Python is smart enough to just treat it properly? Why isn't it actually doing it well? So there's the dot product. There's a dot product between x and w. So and then we're adding b1. And that is giving us x1, z1, sorry. So pretty print tensor. So z1 has this shape. Z1 has this shape. That is odd, isn't it, though? Because that it's odd. Is it odd? Is it what we want? You know, I think that's fine, right? So what we're doing is, so we're essentially taking, yeah, you're taking x and then doing a dot product between x and w2. Because it's of size 10 and it's essentially a row and it's a column. Actually, what this is doing is just, so it's just kind of going and kind of multiplying each these to the first column and adding them up, right? And then it's the first element and blah blah. You kind of do like row column row column row column. Yeah, we know how the dot product works, right? We want in that order because essentially essentially what? Then you have W2, it's hidden size, output size, right? Hidden size is 5 though. That ends up being 5, of course, because it's got 5 columns, which is the hidden size. That's, of course, what we want. And then from the hidden size, we're going to the output size. That's why it's hidden size times output size, this other variable. So essentially, with the dot, what you're doing with the dot product, this is something that is interesting because kind of it's got two aspects of it, right? One aspect of it is the interpretation of dot product. Um, and again, it's just, you have to just, in this case, just have to look at it as a transformation mechanism. Mechanism. And the idea is, right, like you're trying to find a conversion of W1 and W2 that leads to the stuff that you want, right? So, but then, okay, then you've got Z1. For all we care, we don't really need A1, but yeah, whatever, right? It in a way, it's supposed to add non-linearity to it. But maybe we could play without it. Because we want this to just go down anyway, right? So we could maybe just first ignore A1. I always thought the B1's already at non-linearity, right? It's kind of not. That's the point, is that actually it's not. That's not true. That's just a bias. That's just because that's a generic linear. Yeah. That's a generic linear transformation. So you want to add that. We've got Z1, then we've got A1. All cool. Now, what we're doing with A1 and now we're taking A1 and we're basically doing the next step, right? So it's a next layer to get there. But it's fine in a way. Point is here that the backwards stuff, it's fine. So we're getting these, right? And then for some reason, we're calculating we're taking A1. So we're taking the transpose of A1 and calculating, let's say I have this A1 right now here. And I'm doing the dot product between these and dz2, which is basically all this different, you know, the probability difference kind of stuff. So it's going to have a lot of zeros. Oh, good. So if I just doing this by hand, like I'll elaborate that in the next session. I'm just kind of running out of time for today anyway. But so we're taking, so this is something that's got a lot of zeros and just like in a couple of places, like a 1 or a -1, just to correct for the mismatch, right, between one probability distribution and the other one. So when we're doing the dot product, it's going to have a lot of zeros and it's just going to have 1 or 2 ones somewhere. Which means it's going to take this A1 and it's going to turn it into something that it's just got like maybe I was thinking about it wrong because A1, look at this, A1 has basically, A1 has a dimensionality that is basically the hidden dimensionality, the hidden size, 5. So this might not translate to just all ones or zeros, that's the point. That's what I would have to simulate next, basically, right? So, because I've got A1 now, an A1. So let's try this. So let me dz2. So let's get a dz2. So give me code to generate a dz2 tensor or array of dimensionality output size it's all zeros, and let's just say it's got like, and it's got a 1 and a -1. Should be able to do that. Size zeros and choice. Okay, cool. That's good. That's good. That's good. That's good. So we're simulating beef between predicted and truth. And so let's just really print these are two. Humans on one. Did it give me its output size? Yeah, its output size, exactly. And now, so now what we're doing is, actually, we're doing the dot product of A1 transposed and DZ2. Why? Because we want that internal dimensionality. So we're doing now, if we're now doing these, so we're now basically doing, taking A1, so we're taking taking these, and then we're calculating the dot product. Let's ignore this M thing here for now. We're going to do these, and we're going to print PW2. So what is it that we have here? I think why is it complaining though? Shape one. I think just because these are arrays. Could it be that I have something wrong in here? It's reshaping and whatnot. So is it that I just need to do this? That's what I thought. It's correct, right? So so A1. I think, whoa. I mean, this seems to make sense, so why is not? Yeah, but obviously that doesn't work. Okay, I'll go ahead at it next time, in the next session. So that's what's not that's not working here. Maybe something wrong in here. How's this with X? Yeah, I had the same problem here, and I was just kind of I was just like doing things like that, but I'm not so sure if that's the right thing to do. You should really just try to kind of do it from first principles, right? And think of what am I doing? So am I really doing this correctly? So A1 makes sense. The way that That's what I would think, and that makes sense. And then because then dz NP power, that's weird. I never realized about this. Okay, doesn't matter. dw2 is these essentially. So the change that we're adding to dw2, it's just this doesn't seem to make sense. Oh, do not reboot. So essentially what we're doing is, if we want to do something like that, we at least need something. So if we're changing dw2, dw2's got dw2 has got basically the hidden dimensionality. So we want something that is of hidden dimensionality, right? So yeah, so kind of well, I'm very struggling here right now, because I don't know if what I'm doing makes sense at all. I don't even know, it's just from a theoretical perspective that makes sense at all. I have a difference. I'm translating this difference to a, and then kind of broadcasting it to the whole W2. It just makes no sense. Why would I broadcast it? I thought you basically just do. I think I need to find another way to come up. So I need to find another way to do these, or to figure out what the correct way. And I want to kind of, in a way, sort of rediscover it, right? Because that's what's going to help me the most. But I think we're not. So just notes for the next time. Doesn't seem to work. Using A1 leads to a broadcasting for W2, which sure it's correct, right? Because we want maybe individual modifications, not something that we just apply to the whole W2. That just makes no sense. Anyway, see you next time.